try to skim through our 500 slides quickly so that you can. So today I'm going to talk with Martin about how we are running MySQL on 3 different platforms at Booking, what lessons we have learned, what pain points we have seen while we are going through that journey. So that's what we are going to talk about. We are going to give a brief about the architecture at Booking. If you came previous years, you already know a lot about that. Then we will talk about how running MySQL on bare metal evolved over the year. Then we will talk about some of the problems that we saw with bare metal servers that pushed us to think of other solutions. Then virtualization came into the picture over OpenStack, and with OpenStack, new storage solutions came into the picture. So we started testing them. We will talk about how we tested those and how we made decisions about which storage to use. And then eventually we will talk about moving some of our workloads to EC2 as a third platform that we support. So this is me. I'm a site reliability engineer at Booking. I worked there since 2018. Previously, I worked as a Linux system administrator. And I have a computer science and bioinformatics background. And since joining Booking in 2018, I have been working in the database engineering team managing MySQL.
Hello, I'm Martin, principal site reliability engineer. I was born in Patagonia, Argentina. My background is in distributed systems and system engineering. I work in multiple fields and also in the academia. That's me in a cleaning room because I used to build software for satellites. So there are bugs running in space that I built, and I joined Booking last year.
Okay, and to give you an idea about what MySQL means to us at Booking, last year we were MySQL rock stars, and that's because we are one of the biggest, if not the biggest teams that reported MySQL bugs in 2022. We have a lot of work with MySQL. It's our main relational database solution at Booking. And we, as Fred said last year, and it is meant as a complement, we test in production new versions. So we have strong support for MySQL. So as I said, MySQL is the main relational database data store at Booking.com. We have thousands of MySQL servers. We group them in over 200 MySQL clusters. Which also we call replication chains, and they run across multiple isolated network environments, and also they run in 3 different regions in Europe. Each replication chain consists of a read-write primary, either using semi-sync replication or group replication with single primary. And it spans out to tens or hundreds of read-only replicas serving read queries. We use multi-tier replication so that we don't overload the primary. I'll show that shortly. And as I said, a typical replication chain spans 3 different regions within Europe. And we also have a completely isolated testing environment with periodic copies of data from production, but that's outside the scope of our talk today. So that's how a replication chain looks like. So applications connect to the primary, which can be in any of the 3 regions. And then we have intermediate replication sources that are replicating directly from the primary. And this gives us the flexibility and the ability to add as many replicas as we need. We have some replication chains that can go up to 1,000 servers or even more sometimes. All of this infrastructure used to run completely on bare metal servers. and over 90% of the fleet runs on local storage, which back in the days was spinning disks, and now we are mostly running on solid state servers. We have network attached storage for some of our workloads that some of our data sets that don't fit on local disks, and each chain have enough redundancy to tolerate server failures, even as a complete region failure. And also it can run in that state for several hours until we recover the failed region or a bunch of failed servers. And seeding new data, seeding new servers with data happens mostly using MySQL native cloning, but we also sometimes use extra backups and rsync. We will focus now on the majority of our fleet that runs on local SSDs. We have three main flavors server flavors that we use. That disk space size varies between 1.7 terabytes to 8 terabytes, and all the three flavors have the same number of CPUs and memory size. A few systems require more memory sizes or stronger or more CPU resources, but those are just some exceptions. But majority of our fleet fits on these three main flavors. So now some of the problems that we saw with bare metal. When we started moving towards a more service-oriented architecture, it means that every service now needs its own schema, and the schema is accessed by only a few applications. If in order to be able to utilize the hardware that you have, you immediately run into the noisy neighbor situation, where you have multiple schemas with multiple applications accessing them, running on the same resource, and sometimes they compete for resources, or a rollout of an application can bring down another application. So that's one of the biggest problems that we have seen. Also, capacity planning becomes challenging, because now you need to do capacity planning for all of these services, all of these schemas, how they are going to grow over the years, and make sure that when you need more hardware than you have in your data center, that you order it on time. Lead time on hardware is usually 6 months, so you need to predict for 9 months in advance, so that you have some window for delays. And cost attribution becomes even harder, because now you need to do cost attribution for slices of servers. You can do that for a single service or a single schema. Horizontal scaling is our to-go way of scaling so far, but it is always at the risk of delayed hardware deliveries. So usually we need to be very sure that we request hardware on time, and that we request the right amount of hardware, which means that you have to more accurately predict how many servers you will need next year, or in September, how many servers you will need in June, for example, and that's very difficult to calculate. And the hardware that we have right now, with the resources it has, is simply hard to get right now, because servers are becoming more powerful, servers are becoming bigger, and I'll show you a very nice picture of how our hardware utilization looks like. Vertical scaling is one of the options that we go to sometimes, but it's not suitable for all systems. We have big systems where vertical scaling is going to be effective, because if you run on 1,000 servers, you can run on 300 servers if you get bigger servers. But that means that your level of redundancy is going to be reduced from 1,000 to 300 servers. So it's not suitable for many systems. If you have a small system that runs on 20 servers, you can do vertical scaling and run it on 5 servers, but that means that you lost a lot of redundancy. And data center expansion is complicated, expensive, and a slow process. So this is a picture of how our CPU utilization looks like. What I want to show really here is that we have all variations. We have some systems that go up to 100% CPU usage, and we have systems that are mostly asleep, not doing anything, and we have the whole spectrum between those. When it comes to memory, the picture is not the same because we try to utilize the memory completely by increasing the size or calculating the size of the buffer, the NODB buffer pool size, to be as close as possible to the memory limit. And when it comes to disk space, remember that I said we only have 3 flavors, but as you can see, some of the systems are basically can fit in memory. You can run some databases on your phone or your microwave, but still you run them on tens of servers in 3 data centers, and the smallest server has 1.7 terabytes. So how to solve that is either to consolidate as many databases as possible of this spectrum on one server, but that exposes you to a lot of problems, as we said, noisy neighbor, and again, utilization might not be good. So that led us to think about virtualization. So what benefit does virtualization give us? So it will allow us to consolidate many systems on the same hardware, but at the same time with very clear resource allocation and boundaries between the servers that would prevent the noisy neighbor scenario from happening. And it also would improve the utilization, since now more services can be running, more MySQL servers can be running on the same hardware. Vertical and horizontal scaling becomes easier because now provisioning is becoming easier and faster because we use pre-baked images. And also vertical scaling is easier because you need just to resize your virtual machine. You don't need to order new hardware and wait for it for 6 months. And it gives us better control over server quotas and cost attribution, because now every replication chain is a separate entity with the separate resources, and you can have control of how many of its quota in terms of CPU, memory, and disk volumes. But virtualization came with its challenges, so we decided to go with OpenStack, a managed solution of OpenStack, which is virtualization, an open source virtualization software. And one of the biggest challenges that came with virtualization is changing the assumption that everything that we have runs on the same platform. So a lot of refactoring of the automation was needed. Also, the rise of OpenStack resulted in having a new backend and a new inventory for servers, and our automation needs to be aware of that to read metadata servers, request servers provisioning, deprovisioning, and so on, and be able to support the transient migration states. So now we run on bare metal. For some time, we will be running in a hybrid setup, and then a replication chain will be completely running on OpenStack. And also Martin is going to cover that, but EC2 was becoming one of the options in the picture. So what we wanted is to make our automation easily extendable to support more platforms. As I said, we have now 250, 260 replication chains, and we will need to migrate tens, if not hundreds of them to OpenStack, and that means that this is not something that you can do manually. We don't have enough engineers to do that, so we have to build a reliable, transparent, and accurate migration plan. And transparent here is a very important word, because it means that applications should not that the migration should be completely transparent to applications. It's a platform change, and applications don't need to be aware of it. Also, a new platform comes with a new compliance requirements. The platform itself needs to be compliant, and also server patching is completely different on virtualized environment. And then the biggest challenge was which storage to use. OpenStack comes with a safe storage, which we will talk about here. So, there were three main storage solutions available on OpenStack. One of them is Ceph, of course, which is the default one. Network attached storage, a high performance solution, and running with local storage. It's equivalent to the instance store in EC2. So here we see that the baseline that we set for our I/O latency or write latency in microseconds, it's 400 microseconds. Anything above that will impact many of our systems, and we won't be able to run. They will take a latency hit, which means that the migration is not transparent to them anymore. We have some systems, as I said, are running on network storage. And for those, we established that the baseline was around 500 microseconds, but the systems that run there can't tolerate that amount of latency. And of course, NVMe is the baseline for NVMe is quite low compared to anything else, but it is expensive and hard to installed, so we can't just move everything to use. We conducted some storage tests. The first test was FIO. It's an open source tool that you can use to do storage benchmarking. You can configure it to write random blocks on the disk to a file, and it measures the latency. And as you can see here, Ceph always stands out as one of the worst, no, always the worst. Always the worst solution. And then we still have some HDDs, so they follow. And then SSDs, which is what we use right now, and NVMe disks. Those are the local storage devices that we use on OpenStack. The next thing is SysBench. We use SysBench. The numbers you see here are the data sizes. So you can see how, for example, here in Ceph, so the buffer pool size is around 100 gigabytes. So once you go above that, the latency spikes. However, when you look at NVMe, for example, the variation is not as big. And for SSD also, it's not as big, which means that when the application is when the application is running queries that would require fetching data from disk, they wouldn't get a big variation in the latency compared to systems like Ceph or rotating disks. Then we conducted some more tests. Those are not tests that we have designed specifically for the migration to OpenStack, but those are tests that we actually run daily on every one of our clusters. So every day we take a replica out of service. We stop replication on it for some time and measure how much time it takes for it to catch up with the replication. We call this the replication load testing. At some point, if the recovery time becomes equal or longer than the replication delay at the beginning, then we have a problem, because new servers might not be able to join the chain, for example, which means that we need to do some kind of job. Yes?
Do you have any special tooling for replication?
So not really. We use the MySQL replication, but we have our, so we use Orchestrator to manage replication topologies, and we have our tooling that we built also to ensure that we are replicating from the right source. And so, for example, replicating from a server that is in the same availability zone as the replica, things like that. So we have some rules that we implement in our automation to configure replication. So we also have a service level objective and SLO for ensuring that replication running for 99.95 of the time all servers in a replication chain.
But no, we don't guarantee the delay. We guarantee that the replication is running.
Yeah, and another test that we run is load capacity test, where we simply push a server to its limits. We increase, our read-only replicas are organized in pools that serve certain applications. And each server in the pool has a weight. So we keep increasing the weight of a server in the pool until it reaches saturation on one of the resources, I/O, network, or CPU. And once that happens, we understand that this is the capacity of these servers. This is how many connections it can handle, how many queries it can handle. And when you run a test like that at the same time of the day on two servers, one running on OpenStack and one running on bare metal, you can get an idea of how much of performance difference is going to be there. And based on these tests, we decided that some systems are suitable to move to OpenStack, and some systems are still not suitable and need to continue to run on bare metal until either the workload has to change, the application has to tolerate more latency, but that would mean that applications might need to be redesigned, for example. So we don't want to put a lot of workload on the applications, so we take those decisions for them. And some of the pain points that we have seen with OpenStack, it's a new platform, so it comes with a lot of new challenges, new problems, things that we have never thought about before. Now, stability of OpenStack and safe, which was challenging, especially in the beginning of the migration. Increased failure domain, so instead of a failure domain of a single server or a single rack, that can take multiple servers down. Now it is a whole OpenStack cloud that can go down for one reason or another. And if that happens, then you lose big portion of your infrastructure. In order to avoid that, we decided to have multiple clouds in each availability zone, and we try to distribute servers from the same replication chain to different clouds. This way, when you lose one cloud, you don't lose a big portion of the same chain, but it is distributed across multiple. Next thing is, do we do lift and shift or do we do optimization? So do we do move everything to the same flavor that we have on bare metal, which doesn't make sense, because now this means that we are not optimizing anything. We are just using the same resources on bigger servers, or do we do optimize while we migrate? And if you remember earlier today, I told someone not to do two things at the same time, just do a migration first and then optimize, or the opposite. But sometimes we have to do that. And we have an increased risk of noisy neighbor, but it is not coming from our MySQL servers competing with each other, but now OpenStack is running other applications, and those applications might cause issues for databases. And of course, the automation refactoring, which took us several months of hard work to refactor everything in our automation to support multiple platforms. Yes, here.
Okay.
Over to you.
My turn? Okay. Hello again. I'm going to talk about the extension to a new platform, but this platform is AWS EC2. So put a question, why not managed service like RDS? Going to cloud is part of the booking strategy to adopt public cloud, AWS particularly. But our current automation, the fleet management tool, what we built, assume that it has full access and full control to a compute platform. like bare metal or OpenStack. So going to RDS is like, it's not the same operational model, different responsibility, different ownership. So we have expertise more in compute platforms. So it's like a logical step for us is to go to the cloud, have a presence there by adopting the compute platform first. So that's quite the context when we decide to go to EC2. And also we have legacy and big databases with our shared databases. So we don't want to lift and shift into RDS and then who's the owner of that database. So we want to, if we are going to support the extension, which is not a migration, but having presence of our pools, our replicas in AWS, we decided to go to a compute platform. And that's why EC2. Yeah. So again, going to a new platform, new challenges. Particularly in EC2, it was about learning about the new platform, all the offering, because the offering, I mean, in the storage, local storage, EBS, the type of EBS or the local storage, the flavor of the instance type, blah, blah, blah. So it's a lot to learn. Then integrate all the new parts in the new platform in our tooling, like as Mohammed mentioned, the metadata, how we fetch the metadata from the new platform, the inventory, how we lead server, how we provision, and everything needs to be adapted. Then adapt our platform to handle the new platform as transparent as possible and with the less pain that we can suffer. That's quite hard because at the same time we are extending to a new platform. We need to integrate new concepts that our automation doesn't have. We will talk about that. Then building new images. I mean, in EC2 you run images like OpenStack, but a different kind. We have pipelines that we build daily new images for all the MySQL version that we support. So basically, we can based on the MySQL version we are running in a cluster, we can fetch the newest image while provisioning. Then it implies also configuration management changes. We rely on Puppet, so it means that going to a new platform implies quite a few or a lot of changes in Puppet. That's quite a pain as well. Then we need to adapt also processes to the new platform. For example, patching servers. How do we patch servers in bare metal? How do we patch servers in OpenStack? How do we patch servers in EC2? How do we patch servers in the new platform? And those things are quite important because a lot of those processes ensure compliance of the new platform. We need to be compliant in all the platforms. So yeah, that's a big thing. A little bit about our fleet management tool. It's written in Python. It relies on Django. It basically exposes a HTTP API and a CLI, which we call the agent. Also, we rely a lot on crons and background tasks. But yeah, those are a few of the actions that the management tool performs. I mean, the whole chain or cluster management, provisioning, deprovisioning, searching instances like inventory control, server flavor management, MySQL version management, and rollout of a new version. So it goes and we set a new version and we roll it out instance by instance from the replica to the master, service discovery, switchover, failover. Yeah, a lot of stuff. Backup and restore testing. So we take backups and we automatically try to restore those backups. Connection management, root password rotation. We use the feature of have two passwords. So schema changes as well. Yeah, a lot of stuff. And this is the initial commit of our fleet management tool. It's September 6,
2012.
Yes.
12 years old.
Yeah, it's quite old. And you can imagine that extending to a new platform means we need to live with legacy code and also with new code, and we need to try to keep it as friendly as possible. This is a diagram of how our provisioner looks like. We have an HTTP API on top. Then we have what we call the pluggable provisioner interface, where basically we at the moment we have EC2, private cloud on-prem. Below that, we have like the low-level interface, which is like the client library to talk to the external provisioner, and then the external world, the platform. So the important bit is like in this layer at the top, basically we have an interface that we need to implement, and every provisioner needs to implement all the interface or just a few methods of that interface to be a new provisioner. Then it talks to the low-level client, and the low-level client talks to the provisioner. In this case, for example, this is our code, our Python code, which implement how to provision, the provision, search, get instance, whatever in EC2, but it relies on an implementation of the client, which uses Boto3, this is the Python library, to talk to AWS. And the same happens in the other cloud. For example, things that we need to implement or can implement in the provisioner is provision, deprovision, list, get, check for errors like for self-healing, also patching. Patching is an action in the interface. For example, we don't patch bare metal through the HTTP API. We have another mechanism to do that, but we patch through the API in OpenStack and EC2. So yeah, for now, let's focus in this part. And this is remember this and this. When we extend to EC2, we need to think that AWS is a new whole world, and all these concepts, this is like a mamushka, a Pandora box that you open, because now you have AWS account. Inside the account, you have multi-regions, then you have VPCs, then availability zone, then subnet, then security group, and then the instance. All these concepts are new to our automation. Our automation only knows cluster name or chain names and environment. And from that, we need to translate to this. So all this translation layer happen here, right? We through the HTTP API, we say, hey, I want a new server for the cluster A in the environment prod. And this guy needs to go and say, oh, okay, this is prod. Okay, for prod, this is the account I need to talk. For that account, oh, how can I get the region? Oh, yeah, then that's a tricky one. We have regions and ACs at booking, which are not compatible with the convention name in AWS. So we have translations there as well. Right? So yeah, all those translations happen here. Then we need to, okay, give me a VPC in that account in that region. Oh, okay, for that region, then give me a subnet. Inside that subnet, do I have a security group matching the cluster name? No, okay, probably you need to create one. Then create an instance and attach the role that you need to attach to that instance. So a lot of the work happens here. And yeah, in order to do this mamushka, this is quite hard. It was super tricky at the beginning because what we call region at booking is what AWS called AC. And that generated a lot of issues in our tooling and also when we talk, right? Because we were talking about two different things. So we needed to standardize that somehow. So yeah, all those conversions happen in this layer. And now our automation is able to provision successfully here in multiple accounts in multiple regions with no problem. At least I think so. Yeah. Now, okay. Now we are able to go to the cloud. We know how to do it, right? Now, which instance type do we use? So for choosing our flavors, our automation has the concept of flavors, so we have different kind of flavors per practitioner. We took this approach. Try to find the minimum number of virtual CPU and RAM needed to run the workload that we have. Start from everything available in AWS, then go to something that is similar to what we know that should perform in some particular way, similar to our bare metal. Then we try memory optimized instances, which are quite better and require less CPU because the workload that we are moving there are not CPU intensive. Then we try, at the beginning, we tried everything with EBS. We decided everything with EBS. We had coded a size, and we start provisioning. But then we say, why we try local storage? Because there are some instances with local storage. So we start with this guy with approximately 1 terabyte, and the other one 4 terabyte almost. And it worked. It was really good. But then we said, can we go smaller in instances, keeping quite the same performance? And we tried the I4I large, and we failed. And because it couldn't hold the replication. Basically, it worked, but couldn't hold the replication. So we say, okay, we need to go a little bit higher than that. And we choose the X large, and that was okay. Then we decided to say, okay, AWS has cheapest instances, which are all generation, which are quite similar. So we tried, and it worked. So we were following these optimizations, and we arrived to this conclusion that for our workloads, yeah.
Just finish.
Okay, for our current workloads, what we are doing, if we run local storages with reserved instances, it will be much cheaper than running EBS. I mean, EBS has some benefits because it's network storage. You can deprovision the instance, spin out a new one, and attach. But it's way in our cost attribution calculation was like double the cost. Yep.
Were you optimizing just for ability to replicate, or also for ability to support some other workloads?
No, to support all the workloads. But this was the factor that we decided to say, no, we cannot use that instance because we can't even hold on the replication.
Yeah, sure. We're just optimizing the ability to support replicate.
Yeah.
But with local storage, the instance can also disappear anytime.
No, because those special instances has like a local storage, which is a disk, apart from the root volume. You have root volume and data volume, and the data volume will persist until you terminate the instance.
And even if the instance goes down, we have enough redundancy to tolerate one instance going down.
On GCP, it can
Ephemeral disappear.
anytime.
No, we are at this moment we are running everything on demand, which is the most expensive way of running it. But we are considering going to a reserve instance where you pay in advance and you keep that. There is another alternative, which is spot instances, where that's super cheap in comparison to this, but you receive a signal and you have as much as 2 minutes to evacuate the node. Otherwise, they kill you.
AWS doesn't run migration, live migration, while GCP does.
Then, continuing with instance type, until now we decided that Docker storage is a good candidate for our workloads and also for the price. And then we try EBS because okay, we started with EBS. What happened if we try to do some optimization there? And we decided that only EBS is going to be used with the biggest clusters, more than 7.5 terabytes. We don't really, for the current workload, we don't really need high IOPS, so it's okay. And we realized that it's cheaper to use GP3 rather than IOPS 2, which is give you more throughput and IOPS and bigger sizes. Because it's cheaper. GP3 is cheaper. It has a limit of 16 terabyte, but with a little bit of engineering, we overcome a problem. What happens if we have a chain with 26 terabytes? We can put like an array of 2 EBS of 16 terabytes, and we're done. And we are doing that for big chains, and it's quite cheap. It's transparent for MySQL, and our provisioners support that. But yeah, that's if you are using EBS, probably you can consider something like this.
It also increases your right.
Yeah, indeed. Just to describe, the current workload that we have in EC2 are mostly, there are 100% reads, and mostly for big data, reading from MySQL and moving data to other places. We have not, our automation is not allowed to promote primaries there yet. So that's something to consider as well. Well, with the heuristic that we have done, we arrived to this matrix representation of how to choose a flavor based on the gigabytes of the cluster needed. So yeah, this is what we have achieved. It's a heuristic based in our workload and our sizes. When we do this selection, we calculate a safety factor. We multiply for some extra. Okay. And yeah, and that's why we set the flavors. Yep.
For the older generation boxes, how much lead time does AWS give you?
We don't know. Yes. Good question.
How quickly could you transition off?
Super quick. So, I mean, we don't want to do this manually. I mean, this is okay, but we decided to put in the automation. So we have a DBA chain on board to EC2 pick flavor, where you give a cluster and it say, okay, this is the recommended instance for you, but you are running another one, so yeah, probably you need to update. In our configuration, this is how it looks like internally. We have a JSON representation with a default provisioner. Server DB means bare metal. And then for every provisioner, we have a default instance type. So in this case, for EC2, I use the one that the tool recommended me. Also, this execution is just for a suggestion, but we can put a flag there to say, do the update in the configuration. So then the automation, the next time that provision a server will provision with the new flavor. And yes, with all of this, we were able to extend this running in EC2, and they are part of a bigger cluster. This is an intermediate master in EC2, and the read replicas taking replication from that. Then there are, I think, on-prem there. So yeah. So the whole extension work. And yeah, these are some graphs which show that the performance is quite similar with the instance that we choose and what we have at the moment. The application line is in the same parameters. The I/O utilization is quite similar, not really spiky. CPU looks quite similar as well. Yeah. And then an extra thing, I mentioned that something important for us is to migrate to the new platform or to extend to a new platform different process. One of those processes is patching. In EC2, we decided to use an API call which is replace root volume. There's a typo there, which is quite handy. It allows you to replace the image of the running instance while keeping the data volumes. So basically you say, okay, update yourself to the new image. This is the new image, and that's it. And I put like it takes actually like 90 seconds to do all the process. So we can patch instances quite fast. And this is the code to patch. This is valid code. So it's 4 lines of Python, and you can replace your not your whole fleet, but one instance. You put a for loop there, and you have the patching in the whole fleet. So yeah, and it's quite fast. We are considering now to do, we are doing this quite live. We are considering doing this kind of actions in background, but yes, we are not there yet. And again, pain point and future. New platform, new concept, new issues, new challenge. In EC2, it was mostly about flavoring. That was kind of a flavoring and cost. There are 2 variables that sometimes go in the opposite directions. Discover wrong and unknowns in our own automation or our own environment. For example, how we handle environment, how we handle AC, regions, those new concepts are tricky. Automation refactoring. Cost in AWS can skyrocket super easy, so be aware of that. Hard to keep with the updates in AWS. AWS release new instance or deprecate instances, and it's hard to keep track of that. And then, yes, for the future, we are planning to investigate about reserve instances for the whole fleet once we run capacity tests properly based on the workloads, and probably evaluate spot instances for some of the workloads. It's not going to work for big chains that need to a few hours or days to catch up, so that's not going to work. But for a smaller database, it could work. Then define new workload profiles, because we are having new workloads and we need to discover the target reliability for those workloads and start setting objectives based on that. Probably 99.97 writes is not needed for the workload, so we can lower those and have some reliability issues. Yes. And questions. It's late, so.
Yeah, we will be
Yeah,
here
we will
tomorrow
be
if you
around.
have questions.
Thank you.
Okay.